Okay, so let's give this a whirl. Luckily, the A and B are where the math is, and then C actually is pretty nice and simple. So most of this, all the work is going to be in A and B. So for this, so you're going to be getting numbers. So I'm going to go on ahead and make up some numbers here, and I hope I'm going to mix them up that make them really, really nice and simple. For example, our mass is going to be 4 kilograms. Our height, L, is going to be 8 meters. It's a super tall triangle. Theta is going to be 30. I don't know if you guys are using degrees or radians, but I'm assuming degrees. And the distance between the mass and the spring is going to be 0.5 meters. And I know for gravity on your formula chart it said 9.81, but for the purposes of today and to make typing in calculators easier, we're just going to round that off at an even 10 just for the sake of this. The other thing we're going to do is we're going to have our spring constant be 0.25, and I think that's Newton meters? No. Meters, Newton? It's something. It's some unit. That's great. But you might see me sometimes using that as a fraction just because I like fractions. So here we are with this stuff. Now it looks like for A, what they want to know is the final velocity of the block after it goes through a distance d. Well, let me get my laser out. So up here, we have a certain type of energy. It's not moving, so it's just potential, gravitational potential energy. And as it goes down the triangle, it gains speed and loses height, but it still has some height. And so we're going to call this, for this point, height 0. And so at the very end, it's going to have all kinetic energy. Now, I saw how your professor was doing this with setting it equal to work and saying all work is equal to 0 because you're not adding any energy to this. I teach it a little bit different. Does this move? Because I had the same problem last time. I thought I got it to move. Okay, that moves. Okay, well, I'll figure this out. There we go. Okay, so this is what I do. I do any initial energy equals any final energy. And it's what your professor has been doing, but he's been doing it through work and things like that, but it really comes out to the same thing. And I really like doing it this way because I like to think about what happens before the motion, and that all goes on this side. And I like to think about what happens after the motion, or after what I really care about, and that goes on this side. And for a system like this one where like it's just moving because gravity exists and like no one's like pushing it, no one's doing anything, this will always, always, always work. And so I'm going to do this, and I'm sorry if it throws you off, but I really feel like it's just honestly a little bit easier. And so we're going to have initial kinetic energy for all these problems. We're going to have initial gravitational potential energy. We're going to have initial elastic potential energy. And we're also going to have that over here, only it's going to be final. Let me get my pin out. My final kinetic energy, my final gravitational. Sorry, the dog is going, it's no big deal. And then the final, oh, that's an F, an E, not an F, there we go, final elastic potential energy. Well, for this very, very first problem, we won't have any elastic energy, so I'm not even going to write those down. And initially, the block is not moving, so my initial kinetic energy is 0. My initial gravitational potential energy, well, that equation is mass times gravity times height. We're not at all dealing with elastic. And at the very end, we're going to set the height of the spring for this specific problem, for just part A, as 0. Let's go up here and look at that. we're going to set this line right here as my height 0. So it's just going to make it a little bit easier for us. And so that means that when it hits the spring, when it's gone all the way through D, we have kinetic energy. Oop, I forgot the M. And that'll be our final energy. We won't have any gravitational potential energy because we just said that height was 0, and so that really helps us out. And since it hasn't hit this, I mean, it just barely is touching the spring here, we're kind of focusing on like right as it touches before it even starts to compress. And I know it's kind of hard to think of that as 2 different times, but bear with me there, they're 2 different times. So we're going to have 0 elastic potential energy. Oops, that doesn't work. Ooh, that's fun. Sorry, I'm still learning how to use this thing. And so really, this gets us to a really simplified problem. Mass times gravity times height equals 1/2 mass times the final velocity squared. Now it might be tempting to say that your height is L up here, but that's not exactly the case since we're using that line that I just drew as height 0. And so how we do that, this angle right here is also this angle right here, so we're just going to use some SOHCAHTOA. And I don't know how much you remember from pre-calculus or algebra 2, or geometry actually, but SOHCAHTOA just helps us with right triangle problems. S is sine, it tells you about opposite leg and hypotenuse. C is cosine, it tells you about the adjacent leg and the hypotenuse. T is tangent, it tells you about the opposite and the adjacent, and it's just helping you with ratios. Since we know the hypotenuse, and we're trying to figure out if this is the angle I'm talking about, this leg is the opposite, so that means we're dealing with hypotenuse and opposite. That's going to give us sine. So that helps us know what we have to do. And so for this problem, oops, helps if I change to a pen, H is D sine theta. And we got that saying sine of theta was opposite, the height we want to talk about, over hypotenuse, which is D. We just reorganize it, get to that equation, we're good to go. Now I'm going to start plugging in numbers because that's where most physics students feel in their happy place when there's numbers in the problem. And so let's move on and put some numbers in this. My mass, what I said, it helps if I'm not on that. My mass is 4. Oh, I have it written down over here. Okay, great. My mass is 4. Gravity is 10. And my height is 0.5 sine 30. I don't know why I'm writing this so big, but I am. Half, again, mass of 4, and the velocity, final velocity squared, which I don't know. Okay, well, I used 30 degrees on purpose because sine of 30 degrees is a half, and a half times a half is a fourth. Well, 4 times a fourth is 1, and so trust me, if you type this in the calculator, you'll get 10 on this side because that all cancels out. And half of 4 over here is 2. And so we have 2 times our velocity squared. Well, 10 divided by 2 is 5. And so my final velocity is just the square root of 5. I'm going to leave it as that because we're going to be using velocity squared a lot, so 5 is just going to end up being there. Your teacher might want you to actually go ahead and perform the radical. I think the square root of 5 is like 2.2 something. If you get something like that, you know you're on the good case. But that is how we do A. Pretty much all you have to do, and we're going to be doing this a lot in the other problems, is I really think that if you focus on what energy you have before the event and what energy you have after the event and set them equal to each other with your initial kinetic energy, your initial gravitational, your initial elastic, put all those in there. Then with your final kinetic energy, your final gravitational potential energy, and your final elastic potential energy, and that's where we got right there. And then just simplify it from there. It would be helpful to change where you have your height reference. In fact, we're going to change the height reference on the next one. Remember, for this problem, we put our height right here. We said that was our reference level 0, so we didn't have to deal with having, if we didn't set this height at 0, then when we came down here, we would actually have a final gravitational potential energy, and it would just be something more that we would have to calculate. And so we're trying to change those reference levels so that we don't have to deal with it if we don't need to deal with it. And that's pretty much where we're at. We don't want to deal with it. Okay, so B is the fun one, and I say that very sarcastically. So for B, and let me turn over the page on my notes. B, we're trying to find the max compression of the spring, which I'm going to call delta X. You'll also see it in your professor's notes that it's delta X in there too. This is the one where it gets into the quadratic formula. I'm going to teach, and I don't know if he gives you the quadratic formula, but I'm going to give you a song that'll help you memorize it. Because I require that my students memorize it, so I don't know if he's going to require that or not, but It Goes to Pop Goes the Weasel, it's a great song. That's what you have to look forward to at the end of this problem. We will get to that at the very end. So for this one, okay, I'm going to draw I hate going up and down, so I'm going to draw this thing again. Let's zoom out a little bit more. Okay, so here we have our triangle. It's height L, theta here, spring, and now the mass is right up there. I'm not even going to deal with D anymore. And let me see, where did I say the, okay, so for this one, even though we don't know where it is, we're going to set our height reference level where the compression stops. Because that means when the compression, when the mass has stopped moving on the spring, then A, it stopped moving, so we don't have any kinetic energy, and B, if we set that height, even though we don't know, well, I'm not going to write an X because that's going to be confusing there. Even though we don't know what that height is, it's still going to be a 0 if we put that as the height level. So that's what we're going to do here. So as I said, I'm a big fan of let's get the pin out. My initial energy is equal to my final energy, which is what your teacher's doing. As I said earlier, he's just using work in there, which is unnecessary. So again, my initial kinetic energy, my initial, that's an E, my initial gravitational potential energy, undo, and my initial elastic potential energy. And that's going to be equal to final, and I'm just going to use some really shorthand here, final kinetic, final gravitational, and final elastic. Okay, so I like to write all those out so I kind of have a template of what I actually wrote, because if not, you're going to put down a lot of zeros, and I get lost on what I wrote down, so that's why I go ahead and do all that. Okay, so my initial kinetic energy is actually going to be using the velocity we just found in problem letter A. So that's a half. My mass is 4. My velocity is the square root of 5, and we square that. My initial gravitational potential energy, okay, so if it starts here and comes to here, let me change that pen color so it looks different. If it starts here and comes down to here, that's delta X. And just like last time, we still have this angle right here. So this height is going to be delta X sine, sine theta. This thing should read my mind when I actually want to move and when I want to type. That'd be helpful. But that is all there. So that's going to be mass, which is 4. gravity, which is 10. Don't forget for you it's 9.81, but I just like the 10 for right now. It makes it super quick. And my height is delta x sine 30. And at this point, there is no compression of the spring, so there is no elastic potential energy, at least initially. Okay, and now we get to a whole bunch of zeros. I like those. Let me zoom out a little bit so we can hopefully get all this on one screen. Okay. Now my kinetic energy, if the spring is completely compressed, the block stops moving for like a half a second before, not even half a second, but like a split second before it starts going back up. And it's that split second that we focus on, and so the final kinetic energy is actually 0 right now because it's not moving. The final gravitational energy, well, right then, it's going to be at our reference level. So the final gravitational energy is also 0. Now the elastic energy, that's going to be a half times the oh, I didn't make it small enough. A half times the elastic potential energy, which I think I said was a quarter. Now I'm kind of regretting that, but we'll bear with it. And it's the length it was compressed squared. So let's go through and kind of try, not we're still going to do the quadratic formula. For a second I was like, maybe we don't have to, but we're going to have to. So let's go through this. Okay, a half times 4 is 2, square root of 5 squared is 5, 2 times 5 is 10. Okay, 4 times 10, and don't forget sine 30 is a half, that's going to be 20 delta x plus 0, 0, equals 0, 0. A half times a fourth is an eighth. I think that's my phone going off. It's totally okay. Delta x squared. Now what we're going to do is we're going to get all of these to one side of the equation. I'm just going to subtract the eighth delta x squared over. So negative an eighth delta x squared plus, and I'm going to reorganize this to be 20 delta x plus 10 equals 0. Now this might start ringing a bell. It might, if it doesn't, that's totally okay. But this is in the quadratic formula, and it's in the format of it for ax squared plus bx plus c equals 0, with negative eighth being a, 20 being b, and 10 being c. So you get to listen to my tone deaf singing, and I know you've been looking forward to it this whole entire time. Think of the song Pop Goes the Weasel. And that Pop Goes the Weasel is how you memorize the quadratic formula. Hopefully you don't have to memorize it, but just in case, you're going to have a little way to get it. And it goes like this. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to do it one more time just so you can get it. I mean, it's going to be stuck in your head. It's going to be great. You're going to shower and think of this song. Negative b plus or minus the square root of b squared minus 4ac all over 2a. My mom's giving me a look right now, but it works. I trust, it works, it works. And so what we're going to do is we're just going to pop those numbers in, pop, 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 and we will get out our answer. Now I'm probably going to have to pause and do some calculations here because I did not pre-calculate this. But if we have negative eighth, well, that's just a positive eighth plus or minus the square root. Well, an eighth squared is a 16th. No, hold on one second. I'll look at you in a second. I might even just pause this. A 16th minus 4 times, oh, I was doing 1/8 as b when it was totally 20 that was b. That was probably confusing because you're an intelligent person and I did not follow along what I was going to do. Okay, b is 20. b is 20. Ugh. Negative 20 plus or minus the square root. 20 squared is 400 minus 4 times a times c. Well, okay. 4 times c is 40. 40 divided by 8 is 5. Okay, so actually the 8th didn't end up being terrible. And that's all over 2 times negative 8th, which will be negative 4th. We'll get to that. Oh, this actually isn't that bad because you calculate that out. We're going to get negative 20 plus or minus the square root of 395 over negative a quarter, because 2 times negative 8 is negative a quarter. I'm going to pause now and do some calculations, and I'll resume. And I'm back. Okay, so negative 20 plus or minus the square root of 395 is about 19 point, I'm going to round that to a 9. I don't know how many significant digits you need to go to. I'm going to be lazy and just go to the first decimal. But it was really 19.87. Divide that by a negative a quarter. We'll like to do the top first and then divide by the bottom. Or sorry, do the numerator first and divide by the denominator. You can tell I'm really into vocab. Negative 20 plus 19.9 will be negative 0.1 divided by, is that? Yeah, divided by negative, did I do this right? I did. Are we going to get 2 answers? I'm going to pause. Okay, I figured out my mistake, and I messed up somewhere around right here, because the issue was it was negative for a C, but with A being negative, a negative times a negative is a positive, and so that should have been 400 plus 5 instead of 400 minus 5, making this 405, making this number, hold on, I can get that super quick, not even going to get off the, oh, maybe I, let me just get to the calculator on my other phone. It takes, okay, 405 square root, 20.12, so that looks a lot better. Does this erase? Okay, it's not letting me erase. I'm just going to have to cross it off, sorry. Which makes this a positive 1 divided by negative 1/4. Well, a positive divided by negative is a negative, and we can't have a spring that's compressed a negative distance, because negative distance doesn't really matter. So that's why I was kind of pausing for a second. I'm like, oh, we're going to get 2 positive answers. What happened? But this will give you a negative answer, so it's not a good answer. So we're going to move down here and do the other case, because that was the plus, that was the plus or minus. We did the plus case, negative 20 plus 20.1. We got the positive 0.1 here. So now we're going to do the minus case, where it's negative 20 minus 20.1 over negative a quarter. That is negative 40.1 over negative a quarter, which is, although these 2 negative signs cancel out. And anytime you divide by a fraction, you flip it, or you flip the fraction, it becomes a multiplying problem. Or you can put this in your calculator, which is what I'm going to do, but I'm just letting you know that's what I'm doing in my head. And so 40.1 times 4 is 160.4, which is a lot for a for a spring to be compressed, but with the numbers I have, that's the answer we got. B is done. C is like a wave of relief after this, because the whole thing is frictionless. The question on C is, after it rebounds, where does it end? Well, if there is friction, it wouldn't go up as high, right? Like that's, I mean, we've all ridden roller coaster rides. You can't, not roller coaster, like those swinging rides, like you won't swing back up to your original height. But that's because we have air resistance, we have friction, we have things like this. This is a frictionless incline. That sucker is going all the way back up to height L because it's frictionless and there's nothing to slow it down. It's going to. Energy is going to transfer all of its energy into the gravitational potential, and it's going all the way back up to L. So, gosh, if you've hung out for these 25 minutes, I really hope this helps. I am free most of the day tomorrow. I'm having lunch with some friends, but if you do need some more help, let me know, because I'm pretty much just eating lunch with some friends tomorrow, and that's pretty much it. So give me a text if you need anything. You'll be getting a text of, I hope you enjoy this.